Welcome back to our mathematics series. Today, we're going to be diving into the world of string theory.
Oh, wow.
It's a fascinating idea that tries to kind of bridge the gap between the universe's largest structures and its tiniest building blocks.
Yeah.
You know, those fundamental.
Yeah, it's a truly ambitious theory. It's attempting to explain everything from the forces of nature to the very fabric of reality itself.
Right. And underpinning it all is some seriously mind-bending math.
Oh, yeah.
You've probably heard that in string theory, the universe isn't made of point-like particles, but tiny vibrating strings.
Right, and just like different vibrations on a guitar string can create different musical notes, different vibrations of these fundamental strings produce the different particles that we observe.
So instead of a cosmic symphony orchestra, we've got a cosmic string quartet.
Right.
But today, we're not just listening to the music, we're unpacking the math behind those vibrations.
Okay.
We'll be using some articles on string theory and conformal field theory as our guides.
Sounds good.
Are you ready to delve into the depths of these mathematical concepts?
Absolutely. Let's unravel the symphony of strings.
Okay, so to really understand the math behind string theory, we need to start with this idea of conformal field theory, or CFT.
Yeah,
I have to admit, it sounds a bit intimidating.
sure.
What is CFT? Why is it so important for string theory?
CFT is it's a powerful mathematical framework,
Okay.
and it helps us understand systems that are invariant under conformal transformations.
Okay.
So transformations that preserve angles. So imagine stretching or shrinking a rubber sheet, right?
Okay.
The shapes on the sheet might distort, but the angles between the lines stay the same.
I get the rubber sheet analogy, but how does this connect to string theory?
Yeah.
Strings aren't exactly rubber sheets, are they?
Well, as a string moves through space-time, it traces out a two-dimensional surface called a world sheet.
Uh-huh.
It's like the string's footprint in space-time. And here's the key. This world sheet can be described using the tools of conformal field theory.
So CFT helps us analyze the footprint of a string as it vibrates through spacetime.
Yep,
That's pretty neat.
it is.
And this brings us to another crucial concept, the conformal group.
Yeah.
Think of it as a collection of mathematical operations, including things like translations, rotations, and dilations.
Right.
This is just a fancy word for scaling things up or down.
Exactly.
So we can move, turn, and resize shapes, but the angles stay the same.
Precisely. Now, here's where it gets really interesting.
Okay.
In two dimensions, the conformal group becomes remarkably powerful,
Okay.
possessing a much richer structure than in higher dimensions.
Mhm.
This is a major reason why string theory's two-dimensional world sheet is so significant.
So this seemingly simple idea of preserving angles unlocks a whole new level of mathematical sophistication in two dimensions.
Exactly. And within this framework, we encounter these fascinating entities called primary fields.
Okay.
They're like the fundamental building blocks of our CFT,
Okay.
each with specific transformation properties under those angle-preserving transformations.
Okay, so primary fields are like the well-behaved citizens of the CFT world, following the rules of conformal transformations.
Yeah, a good way to think about it.
Okay.
Then we have their more complex cousins, the descendant fields.
Oh, okay.
Which are essentially derivatives of primary fields. Their behavior under transformations is more intricate.
So they're like the rebels who push the boundaries of conformal transformations. Are they important, or are they just causing trouble?
They are crucial. Descendant fields play a significant role in tools like conformal blocks and operator product expansions, which helped us calculate how those fields interact in a CFT.
Interesting. So there's more to these rebels than meets the eye.
Right.
Now, you mentioned correlation functions earlier.
Yeah.
What role do they play in this mathematical framework?
Correlation functions are essential tools in quantum field theory.
Okay.
They tell us how fields at different points in space-time are related, kind of like a measure of how much one point cares about what's happening at another point.
Okay, so they describe the interconnectedness of spacetime.
You got it.
Okay.
And the beauty of CFT is that it allows us to calculate specific forms for these correlation functions, particularly those involving primary fields. And here's the mind-blowing part. The form of these correlation functions is highly constrained by conformal symmetry, leading to powerful predictions about the behavior of CFTs.
So by understanding the relationships between these primary fields, we can start to unravel the workings of the entire CFT.
Exactly.
Like having a few puzzle pieces and using the rules of the game to figure out the whole picture.
Right.
I like that. Now, before we get lost in the theoretical landscape, could you give me a real-world example of where CFT shows up?
Absolutely. The critical ON model.
Okay.
Particularly the Ising model is a great example.
Okay.
The Ising model is a simplified way to look at magnetism. It shows how CFT, despite its abstract nature, has connections to tangible phenomena in condensed matter physics.
So we have these abstract mathematical ideas in CFT, and they're actually helping us understand something as concrete as magnetism.
Yep.
That's incredible. But now let's bring it back to the star of the show, string theory.
Okay.
I know from the research we've got that the math behind it can be pretty intense.
String theory definitely pushes the boundaries of theoretical physics.
Yeah.
One of its biggest goals is to unify quantum mechanics, which governs the microscopic world of atoms and particles, with general relativity,
Right.
which describes gravity and the large-scale structure of the universe.
Right. And as you know, those two haven't been getting along very well.
That's an understatement. For decades, physicists have been searching for a way to reconcile these two fundamental theories.
Yeah.
String theory aims to be that unifying theory, the elusive theory of everything.
A grand ambition, to be sure.
Yes.
But how does string theory actually go about unifying these seemingly disparate realms of physics?
That's where the concept of the string action comes into play.
Okay.
It's a mathematical expression that encapsulates the essence of how a string moves and interacts in space-time.
Okay.
You could say it's the string's rulebook for navigating the universe.
So if we could decode this string action, we'd understand the fundamental laws governing the universe.
In theory, yes.
Mm.
And just like nature often takes the path of least resistance, the string's path through space-time is also determined by a principle of least action. It always chooses the path that minimizes its action.
So in a way, the string is always taking the most efficient route.
You could put it that way. And this leads us to the fascinating world of symmetries.
Okay?
Symmetries are like hidden patterns in nature that reveal fundamental properties and often simplify complex calculations.
Yeah.
They're like nature's cheat codes for physicists.
That's a great way to put it. So what kind of symmetries are we talking about in the context of string theory? What are these cheat codes that help us understand the universe?
The string world sheet exhibits two key symmetries, reparametrization invariance and well invariance.
Okay?
Reparametrization invariance basically means we have freedom in choosing coordinates on the world sheet,
Hmm.
while well invariance means the theory is invariant under local rescalings of the world sheet metric.
Okay, so these symmetries are basically telling us that we have some flexibility in how we describe the string's world sheet. Sort of like using different maps to navigate the same terrain.
Exactly.
Okay.
These symmetries are crucial for the consistency of string theory
Hmm.
and impose powerful constraints on its mathematical structure.
So they're not just mathematical curiosities. They have profound implications for how string theory actually works.
Precisely. And perhaps the most intriguing consequence of these symmetries is the emergence of extra dimensions.
Ah, the mysterious extra dimensions.
Right.
I was wondering when those would show up.
To move from a classical description of the string to a quantum one,
Okay.
a process called quantization
Right.
requires a specific number of space-time dimensions known as the critical dimension.
Oh, the critical dimension.
All right. And here's where things get truly mind-boggling.
Okay.
For the type of string theory we've been discussing,
Uh-huh.
the critical dimension is 26.
26 dimensions. That means there are 23 dimensions beyond the 3 spatial dimensions we experience every day. That's wild.
It is, and this revelation arises directly from the mathematics.
So we're not just adding extra dimensions for fun, they're a necessary consequence of making the math work out.
You've got it. It's one of the most perplexing and fascinating aspects of string theory. You know, these extra dimensions aren't just some arbitrary addition, they're woven into the very fabric of the theory.
So if I'm getting this right, we started with CFT to understand how strings move and interact. And that led us to this surprising conclusion that there might be more to our universe than meets the eye, literally. But how do these abstract mathematical concepts actually describe the way strings vibrate and create the particles we observe?
Excellent question. Those primary fields we diffused earlier, they play a crucial role here. It turns out that they're directly linked to the different vibrational modes of a string. So imagine a tiny guitar string, and those different vibrational modes are like the different notes it can play.
Okay.
Each note corresponds to a different particle.
So by studying the properties of these primary fields, like their conformal dimensions, we can gain insights into the nature of those corresponding particles.
Precisely, CFT acts like a mathematical decoder ring, helping us decipher the language of the subatomic world.
That's amazing. But I have to admit, all this talk of primary fields and conformal dimensions can feel a bit abstract. Can we maybe ground this in a more concrete example?
Of course, let's go back to the string's world sheet, that two-dimensional surface traced out by the string as it moves through space-time. Picture a closed string, a loop of string, vibrating in a particular way.
Okay, like a tiny hula hoop vibrating.
Perfect. Now that vibration can be described by a wave traveling around the string, this wave can travel in two directions, clockwise or counterclockwise, around the loop. We call these left-moving and right-moving waves on the world sheet.
Got it. So we've got these waves traveling around the closed string, each going in a different direction. Why is that important?
What's incredible is that we can describe both of those waves using CFT. It's like having two sets of mathematical tools, each providing a complementary perspective on the string's vibrations.
So we're essentially using two copies of CFT, one for each direction of the wave, to fully describe the behavior of the string.
Exactly, and it all stems from that simple idea that the string's world sheet is a two-dimensional surface that can be analyzed using CFT. It's a testament to the power of mathematical abstraction. By stepping back and viewing the world sheet from this abstract perspective, we gain remarkable insights into the behavior of the string itself.
This is all starting to click for me, but it makes me wonder, if we're using two copies of CFT, shouldn't they be consistent with each other? It seems like things could get messy if they're not talking the same language.
That's an astute observation. You've hit upon a crucial point for our description of the closed string to be physically meaningful. The left-moving and right-moving sectors of the CFT must be compatible in a very specific way. We call this the level matching condition.
So it's like a delicate balancing act between the two sides of the CFT description. What happens if the level matching condition isn't met?
Essentially, if the level matching condition isn't satisfied, the description of the closed string falls apart. The math no longer reflects a physically sensible scenario. It's like trying to build a house with two sets of blueprints that don't agree. You're going to end up with a very unstable structure.
That makes sense. So this level matching condition ensures that our mathematical house, the CFT description of the string, is built on solid ground. But how do we make sure that the two CFT descriptions are in harmony?
It boils down to how we choose those primary fields in each CFT. Remember, each primary field corresponds to a specific vibrational mode of the string, those different notes it can play.
Right. So it's like we're trying to create a harmonious melody by selecting the right notes from both sides of the CFT orchestra.
That's a fantastic analogy. The level matching condition is all about creating a harmonious mathematical symphony from the two CFT descriptions.
This is truly mind-blowing. I'm starting to see how deep this rabbit hole goes. We've covered so much ground, from the foundations of CFT to this intricate level matching condition in string theory. It's incredible how these seemingly abstract ideas can have such profound implications.
It's a testament to the power of human curiosity and our drive to understand the fundamental nature of the universe, but we're not done yet. We still need to explore how those extra dimensions we discussed earlier arise naturally from the math and delve into their potential impact on our understanding of the cosmos.
All right, so we're back and ready to tackle those extra dimensions. You mentioned they emerge naturally from the math of string theory. How does that actually happen?
It all goes back to those vibrational modes of the string.
Okay.
When we quantize the string, basically moving from a classical description to a quantum one, we discover that those vibrational modes are quantized as well. They can only exist at discrete energy levels, much like the energy levels of an electron in an atom.
So it's like the string can only play certain notes on its cosmic scale.
Exactly, and the spacing between those energy levels is determined by the string's tension, which is related to a fundamental constant in string theory.
Okay, I'm following you so far. But how do we jump from quantized vibrations to the existence of extra dimensions?
Here's where it gets really interesting. When we try to quantize the string in our familiar three spatial dimensions, we run into inconsistencies.
Oh.
The math just doesn't add up, leading to nonsensical results.
Wait, so our everyday 3D world isn't sufficient to contain these vibrating strings?
That's one way to interpret it. To make the math consistent, we need to introduce extra spatial dimensions. It's as if the strings need more room to vibrate properly.
So these extra dimensions aren't just some theoretical add-on. They're a fundamental requirement for string theory to make sense.
Precisely. They're baked into the very structure of the theory.
Incredible. But if these extra dimensions are real, why don't we see them? Where are they hiding?
That's one of the biggest mysteries of string theory. One possibility is that these extra dimensions are compactified.
Okay.
Curled up into tiny shapes that are far too small for us to detect directly.
So it's like each point in our 3D space actually contains a tiny, hidden, multi-dimensional world.
Exactly. It's a mind-bending concept, but it's one way to reconcile the existence of extra dimensions with our everyday experience.
Okay, I'm trying to wrap my head around these curled-up dimensions. But if they're so tiny and hidden, how could we ever prove or disprove their existence?
That's a challenge for experimental physicists. One possibility is that these extra dimensions could have subtle effects on the forces and particles we observe. It's like trying to detect a tiny pebble by observing its gravitational pull on a nearby leaf. The effects might be incredibly small, but with precise measurements, we might be able to find evidence of their presence.
This is truly amazing. We've gone from the abstract world of conformal field theory to the idea that our universe might be filled with hidden dimensions curled up at every point. It's a lot to take in, but incredibly fascinating.
It is indeed a journey into the depths of theoretical physics. And remember, we've only just scratched the surface of string theory. There are still many open questions and mysteries to explore.
Absolutely, this has been an incredible deep dive into the math behind string theory, and I'm walking away with a newfound appreciation for the beauty and complexity of this theory. It's amazing how something as seemingly simple as a vibrating string can lead to such profound insights about the nature of our universe.
It's a testament to the power of mathematics to illuminate the deepest secrets of the cosmos.
Well, on that note, I think it's time to wrap up this deep dive. Thank you for joining us on this incredible journey, and we'll see you next time as we continue to explore the fascinating world of mathematics.
Until then, keep those minds curious.